Thank you very much. I would like to thank the organizers for giving me the chance to speak here and making it possible for me to attend it online. So in this lecture series, Anna and I will explain the Igusa's text and their applications. So I will start by introducing these objects and explain the basic geometric properties of them. So let me start with a quick overview, providing some background or motivations for studying them, and also mentioning the main players of the story. So I will provide details afterwards and an example of GL2. So, so basically, given some Shimura datum, which recall that consists of a reductive group over Q and its symmetric space for the real point. So the symmetric space parameterizes a variation of Hodge structures, which gives rise to a Hodge co-character, and whose reflex field is a number field called E. So this datum also gives rise to a tower of algebraic varieties defined over E and labeled by compact open subgroups of the adelic points, finite adelic points of G. So these are the Shimura varieties. So the basic question we wish to understand is the geometry of these varieties, as well as their cohomologies for the purpose of studying the Langlands program. And the story of Igusa's text begins when Schulze, 2025, has the nice idea that you can study the cohomology of these Shimura varieties using a p-adic period morphism. So, namely, analogous to the complex case where you can pass to the universal cover of the Shimura variety and look at the map to the period domain using this variation of Hodge structures. In the p-adic context, you can define an analogous map to a period domain using the Hodge state periods of the universal abelian varieties over the Shimura variety, at least in the Hodge type case. So for this, we fix some p-adic place of the reflex field and look at the completion of E at this place. And we fix them away from P level, K upper P. Then one can first pass to analog of the universal cover in this case. So you pass to an infinite level at P of the base change of these Shimura varieties to this local field. And we denote it by SK upper P. Then this Hodge state period map would be a map from SK upper P to a partial flat variety, parameterizing filtrations of type mu inverse, where mu is the Hodge co-character. So, and so this map, to make sense of this map, one has to work in an analytic context. And later we will view this as a map of pre-sheaves on perfectoid spaces. So, so for this purpose, sometimes we will use an upper small diamond to denote that these are tested on perfectoid spaces. Similarly here. And so later, Cariani and Schulze used this map to study the cohomology of Shimura variety, where the basic idea is that one can use a Leray spectral sequence for this map. And there they discovered that this geometry of this map is very interesting in the sense that, contrary to the complex case, so there is a stratification on this period domain where the fiber of the map are where this map becomes a vibration from on each stratum. And if you go from stratum to stratum, then the dimension of the fibers can evolve. So this stratification comes from a map from the flag variety to the stack of G-tossers on the Fargues-Fontaine curve. So this map is usually called Bouvier-Laszlo map. So and the stratification comes from the natural stratification on Bungie corresponding to the isomorphism classes of these G bundles. And so during the same time, around the same time, Fargue and Schulze are writing down their program for geometrizing the local Langlands correspondence using the stack Bungie as so where they use tau sheaves on Bungie as an incarnation of the automorphic side of the local Langlands correspondence. So where in order to state compatibility of the local Langlands correspondence with the global ones incarnated as informations of cohomology of the Shimura variety, one would expect that there is a sheaf on Bungie that encodes the arithmetic information coming from the Shimura variety. So one natural guess is that if you look at any local system, automorphic local system on the Shimura variety, then its push forward along the Hodge-Tate periodic map to the flag variety will descend to Bungie. So for example, we fix some p-adic or torsion coefficient ring lambda, and this trivial sheaf, this push forward of this trivial sheaf should descend to Bungie. So it is in this context that Schulze made a more stronger conjecture that this phenomenon of descent already happens on the geometric level, in the sense that the Shimura variety itself should descend to Bungie. So namely, there should be some stack, depending on this Shimura datum, living over Bungie, where if you pull it back along the Bouvier-Laszlo map to the flag variety, it should recover the Shimura variety. So this is what we call the Igusa stack. So the conjecture says that there exists a Hecker equivariant Cartesian diagram as above for all Shimura datum. And so the status of this conjecture is that this is known in full generality for Hodge-Shimura varieties due to joint work with Patrick Daniels, Paul van Hoften, Daniel Kim, and Daniel. So where in my thesis, I did it for certain PL type Shimura varieties, and then in its joint work, we extended to Hodge type Shimura varieties that on the good reduction locus, and Daniel extended to a result for the full Shimura variety. And he also proved uniqueness and functorality of the construction of an Igusa stack once it sits inside such an Hecker equivariant Cartesian diagram, plus the fact that it's defined over FP. So he will explain this later in this week. So for abelian type Shimura varieties, this is joint work in progress with the same group of people. So this is basically the main players, and later Anna will explain more about the application of this Cartesian diagram. So for the rest of this talk, I want to focus on the construction of this diagram in the case of GL2. Which is already very instructive. So in this case, the symmetric space is the union of the complex upper and lower half plane, and the Shimura variety is the modular curve, which is a familiar object. So let me start by recalling the construction of the Hodge state and Bouvier-Laszlo maps. As I said, I will view the objects as sheaves on perfectoid spaces. So let me denote a perf by perf, the category of perfectoid spaces in characteristic P with the V topology. So which is introduced by Schulze as an analog of FPQC topology for schemes. So then this infinite level modular curve can be viewed as a sheaf on perfectoid spaces by sending S to a set of pairs consisting of an untilde of S over QP and a map from this untilde to the analytification of the scheme. And similarly, you can do the same thing for the flat variety, which is in this case just the projected line. Now, for constructing the Hodge state map, so we want to say that if we are given a map from a perfectoid space to the infinite level modular curve, we want to construct a map from S to the P1 diamond. So in other words, so this map from S to this modular curve specifies an untilde, and then we want to get on the trivial rank 2 bundle of this untilde subline bundle inside there. So so this map to P1 diamond also entails choosing an untilde of S over QP, but this one is already specified by the map to Y K upper P. So and also tilting and non-tilting is not very serious issue in defining this map. So let me just drop this sharp everywhere and pretend that S is already characteristic 0 perfectoid. So we write universal for the universal elliptic curve over Y, and then this projection map by F. So we want to mimic the construction in the complex case. So namely, we can look at the relative étale cohomology of this universal family, and then if we tensor it with the structure sheaf of the base, then this gives us a rank 2 vector bundle. But on this infinite level modular curve, this local system, this p-adic local system is already trivialized. So this will be isomorphic to the trivial rank 2 bundle on S. Now we want to construct this filtration. So first of all, by primitive comparison theorem, we notice that so if we write ES as the fiber product here, then this tensor on the right-hand side is also the relative Freutal cohomology for the structure sheaf on ES. So I use a hat to denote the structure sheaf on the Freutal side. So using the fact that S is a perfectoid, this is a priori a Freutal vector bundle, but using the fact that S is perfectoid, there is no difference between Freutal vector bundles and Étale vector bundles on S. So this is also the same as the so the H1 of the push forward from the Freutal side all the way to the Étale side. So namely, we can rewrite the right-hand side as Étale push forward of R nu lower star of O hat, where this nu denotes the projection from the Freutal side to the Étale side here. Now one can use the wonderful fact of Feltings and Schulze that if you push forward the structure sheaf from the Freutal side to the Étale side, then in degree 0 you get the structure sheaf, but in higher degrees you get differentials. With some Tate twist. So now if you plug this formula in to the natural filtration on this H1 given by the slurry spectral sequence, you get the so-called Hodge-Tate filtration. So where you have a sub given by the R1 F Étale push forward of the structure sheaf to the middle term, which is R1 F lower star ZP tensored with OS, and then with the quotient given by the tau push forward of differential forms. So now the middle term is also trivialized, as we said before. So this altogether gives the desired map from S to P1. So let me make a few remarks here. So the first one is that this is analogous to over the complex numbers, where you would take the singular cohomology with z coefficient tensored up to C, and then you have a Hodge filtration on this thing. However, if you look closer at the sequence, you notice that the difference is that for the Hodge-Tate filtration, the differentials appear naturally as a quotient, while for the Hodge filtration, it naturally appears as a sub. So this is the switch of sub and quotient leads to the fact that when we look at the Hodge-Tate period map, the flag variety is labeled by mu inverse, if mu is the Hodge cocharacter. And a second remark is that this map, as in the complex case, is highly transcendental. So you cannot um, define this thing on just the level of algebraic varieties. And it tells you that it's kind of necessary to pass to some p-adic analytic topology. And also from the construction, we see that working with perfectoid spaces is also necessary because we've used the fact here when we rewrite this thing here, we've used the S being perfectoids to eliminate the difference between pro-étale and étale vector bundles. Because to give a map, and even analytic vector bundles are the same in this case. Because to give this map to P1, you really have to find analytic subbundles. Okay, so the next thing is the construction of the Bouvier-Laszlo map. So we're, again, if we are given some perfectoid test object S mapping to P1, diamond, and we want to construct yeah. Sorry. We want to construct the map to sorry, for some reason this pen is not working. Ah. Let me try to do this. I'm sorry. Okay. So we want to construct this map from S to bound 2. So which means that we need to construct a rank 2 vector bundle on the relative Fargues-Fontaine curve over S, which is defined as taking the adic spectrum of the width vector applied to R plus if my test object is of the form spar R plus, and then remove analytically the fixed points of the forbidden section, which is the vanishing locus of P times the Teichmüller lift of a pseudo-uniformizer. And then quotienting out the action of forbiddenness. So for this, so notice that the point from S to P1 diamond specifies an untilde of S over QP, and then together with a line subbundle of the trivial rank 2 bundle on this untilde. Then using this and the fact that this untilde will define a closed Cartesian divisor on the Fargues-Fontaine curve of degree 1. So this Cartesian divisor corresponds to a line bundle on the Fargues-Fontaine curve, and for which we have an exact short exact sequence given by the structure sheaf mapping to this line bundle, which we call O of 1, and then to the structure sheaf of this untold. And then we can do 2 copies of everything, and now use this subline bundle to pull back the sequence. And then the middle term will give us a new vector bundle of rank 2, and this is the desired map from S to bond 2. So this map is called a Bouvier-Laszlo map because from the description or this construction, we see that the middle term is a modification of the trivial rank 2 bundle using a procedure that is close to Bouvier-Laszlo gluing along this divisor. However, there is another way of interpreting the construction of this map in terms of p-divisible groups. So we offer this alternative description because it will become relevant to us later. So, so we said that we're using the V topology here. And one benefit of that is that the test object can be chosen so to be a very simple form V locally. So in particular, the V topology has a basis where given by the so-called product of points. So namely, the test object will be of the form spar R plus, where R plus is a product of absolutely integrally closed validation rings. So and so inside R plus, there's a subring of power-bounded elements, which is product of this ring of integers in these algebraically closed fields. So then, so on such a test object, the map to P1 diamond actually is also the same as choosing an untold of S as before, and then giving a p-divisible group over SPIF of R circ sharp. Together with the trivialization of the Tate model of the p-adic generic fiber of this p-divisible group. So this essentially comes from the classification of p-divisible groups over OC given by Schalze-Weinstein according to their Tate model and together with the Hodge-Tate filtration on the Tate model tensored up to C. And it actually works for these products of rank 1 points as well. And so given such data, if we take the Dieudonné module of H, then we can get a finite projective module over the width vectors phi to R circ, and then together with the Frobenius semilinear endomorphism, so, and this endomorphism becomes an isomorphism if you invert some divisor. So therefore, if you restrict this Dieudonné model to a space that covers the relative Fargues-Fontaine curve, and that does not intersect with this divisor, then this endomorphism becomes an actual descent datum that gives you a vector bundle on the Fargues-Fontaine curve, so which we'll denote by E of H. Yeah, so this gives an alternative construction of the Beauvais-Laszlo map. So let me remark here that this vector bundle you get actually only depends on the reduction of H mod P, and in fact only depends on the isogeny class of that. And also, so a second remark I want to alert you here is that you see from this description that both P1 and G do not see the difference between R plus and R third. So so this will become a problem that this will become a point that sometimes causes some confusion when we use this map to define a stratification on the modular curve, so which I will mention in a while. So, so this is the previously already constructed part of the diagram. So now we move on to the Igusa stacks and the full Cartesian diagram. So the key input of constructing this diagram is the result of Serre-Tate, which describes deformation theory of abelian schemes and p-divisible groups over p-nilpotent rings. So this says that if we have a nilpotent thickening of rings on which p is nilpotent, then first of all, the isogeny category of abelian schemes or p-divisible groups over S and R are equivalent. And second, so the category of abelian schemes over R is equivalent to the category of triples consisting of an abelian scheme over S and a p-divisible group over R. And together with an identification of the p-divisible group of A with the base change of H to S. So in other words, deforming abelian schemes from S to R is the same as deforming its p-divisible group. So the same is true if you consider these categories up to isogenies. So, so using this result, so basically this Cartesian diagram for Igusa stacks that we want to consider is just a geometrization of this result in terms of their moduli spaces. So having this in mind, it's not hard to make a definition of the Igusa stack, at least on a good reduction locus, so which I will denote by an upper circ. So this is the free stack on perfectoid spaces that sends a test object of the form spar R plus to the groupoid whose object are elliptic curves over R circ mod var pi, where var pi is any pseudo-uniformizer. And then together with an away from P level structure. And the morphisms are P power isogenies that are compatible with this level structure. And so this construction gives you a pre-stack, and then you do a sheafification for the V topology. So this is well defined, so at least not depending on the choice of the pseudo-uniformizer by Sertate 1. Let me immediately make the remark that I don't know if it's necessary to do V-sheafification. So I would expect that a tau sheafification already suffice to give you a V-stack, but I don't know. So this is basically a question about descending abelian schemes up to isogenies. And then a second remark I want to make is that the stackiness of this moduli problem is rather mild, basically coming from this this level here. So namely, if you pass to away from P, so infinite level away from P, then this thing is actually zero truncated. And the reason is that the moduli problem will already be rigidified by the requirement that the P power isogeny preserves this away from P trivialization of the away from P Tate module. Right. So given this definition, using the moduli problem, it's not hard to get a commutative diagram as a candidate for this Cartesian diagram we wanted to construct. So namely, so we have already the Hodge state map. We have the Beauvais-Laszlo map. And we have a map from the modular curve to the Igusa stack just by taking on a just by taking reduction of the elliptic curve. So namely, from here we get untold of S elliptic curve over R plus mod sharp, and then trivialization of the level K upper P level, and then a trivialization of the Tate module at P. And then you forget everything else, but just remember the reduction of E. So where this var pi is p tilde, and then the away from p level, and then consider this up to isogenies. And it also has a map to bond 2 just by taking the vector bundle attached to the p-divisible group of E0 as explained before. So more precisely, it will only depends on the E0 base change to R steric sharp mod P. So it remains to show that this diagram is Cartesian. So as we mentioned before, so using so the commutativity of this diagram already gives you a map from the modular curve to the fiber product of the two other terms over bound 2. And as we mentioned before, to check that this is an isomorphism, it suffices to check for the basis of the V topology given by product of points. And from there, using quasi-compactness of the Hodge-Tapier map on the good reduction locus versus some properness of P1, you can further reduce to the case where S is where the test object is just a single point. So even single geometric point, so C is algebraically closed. And then in this case, an S point of the fiber product gives rise to a triple consisting of an elliptic curve over C plus mod bar pi untiled over QP. Maybe I just write C sharp. P divisible group over OC sharp. And and an isomorphism between the attached vector bundles of the p-divisible group of E0 versus H by full faithfulness of the construction of p-divisible groups up to isogenies over OC mod var pi to vector bundles on the Fargues-Fontaine curve. You get an isogeny between these two p-divisible groups. And now, so if C plus would be just the ring of integers, then we see that this is precisely the gluing data, which by Serre-Tate theorem will gives us elliptic curve over C plus C OC sharp, and which is a point on the modular curve. So sorry, here you also get the trivialization of the Tate module, and which carries to the trivialization of the Tate module of the elliptic curve you get. So and in general, you can first extend. You will have to first extend the H to a p-divisible group over C plus sharp, which you can do in a unique way because essentially this isogeny will tell you will give you a unique way to modify the p-divisible group of E0 itself and then glue it to H to extend it to C plus sharp. And this finishes the proof of the Cartesianness of this diagram. So again, let me make a couple of remarks. So the first one is that from the construction and the proof, you see that we're mostly using the integral value points of the corresponding formal models of the objects we consider. So you would wonder whether there is a version of the Cartesian diagram on the integral level as well. And this is indeed the case. So in the same work with Patrick Daniel and Paul, we have an integral version um, of the Cartesian diagram for Hodge type Shimura varieties at parahoric levels. Where the statement is that if the bottom row remains the same, you take the good reduction locus of the Igusa stack mapping to bond G and replace the flat variety by a moduli stack of p-adic Stukas at parahoric levels, then you recover the V-sheaf attached to the canonical integral model of the Shimura variety at the corresponding level. So a second remark is that the philosophy of this diagram is basically a Bouvier-Laszlo gluing for the integers, in the sense that the abelian scheme is a module over Z, and then passing to its p-divisible group is a completion at P, and then passing to the isogeny categories is by inverting P. So therefore, so this diagram tells you that we are separating the information of the Shimura variety into a P part and away from P part encoded by the Igusa stack. And since we have this program of doing local Langlands around bond G, so this diagram makes it particularly powerful if you want to study information of Shimura variety at a place. Because if the local Langlands on bond G is known, then it should encode basically all the arithmetic information at P there. And so this philosophy is actually more transparent if you look at the function field setting analogy. And as far as I understand, so this is a work in progress by Peter Delory and Daniel-van-Hoften-Kim-Zhang. So where the corresponding spaces would be on the top row, moduli spaces of global and local Stukas with one moving leg, and on the bottom row, Stukas with no leg on a punctured curve. So let me stress one last thing here, is that another feature of this diagram is that it combines the mod P and p-adic geometry. So So namely, the bottom row, they are naturally the stacks defined over FP, while the top row are objects over QP because of these part of the moduli problem is choosing untils over QP. And more generally, if you consider a general Shimura variety, then the top row will be defined over the local reflex field of the Hodge character. And this diagram makes it clear that all the Galois information at P of the Shimura variety comes from the structure map to this flat variety. Okay. Okay, so in the remaining several minutes, I want to explain one last thing. It's about the Newton stratification I was alluding to from the beginning on the Cartesian diagram. So this comes from the fact that G so the starting point is the classification of G-tossers on a Fargues-Fontaine curve over a geometric point. So where you see that the isomorphism classes will correspond to the Kottwitz set, which is more classically known to classify isocrystals with G structures over FB bar. So in fact, this is an identification on the level of topological spaces if you choose the correct order topology on the Kottwitz set, and using which you can define a stratification on bound G, and pulling back along the diagram, you get a stratification on the whole Cartesian diagram. And so the image of the Hodge state the image of the Igusa stack in bound G will lie in a subset. If I didn't do that before, I will call this map pi Hodge state R. This will be the subset in the Kottwitz set bounded by mu inverse, where mu is again the Hodge character. So, and for any element there, so as we said before, pulling back on the Cartesian diagram, you get a stratification of the whole diagram. So where I switch back to the notation for general Shimura varieties. But what I will do next is just to explain what these stratums are explicitly, again, in the case of modular curve. So where in this case, so in general for GLN, the Kottwitz set will be just given by the Newton polygons of the correct shape. And mu inverse will give rise to some Hodge polygon. And the set BG mu inverse will be the Newton polygons. Sorry, is there a question?
No. Okay, so good. You can continue.
Oh, okay, sorry. All right, so the BG mu inverse will be the Newton polygons above the Hodge polygon. So in particular, in this case, you have two with slopes are 0, 1 and a half. And correspondingly, the vector bundle on the Fargues-Fontaine curve, so which we denote by EB, will be O plus O of 1 versus O a half. And so the stratum in bone G will be just given by the classifying stack for the automorphism group of the corresponding vector bundle. So later maybe this group is denoted by GB tilde. And so for this vector bundle, you get the automorphism has QP crosses. So the V sheaf attached to this topological group on the diagonals. And coming from the fact that this global section of O on the curve gives you QP, and then some Banach space on the diagonal. Sorry, on the upper triangular part. And for O of a half, you get the V sheaf attached to the group of units in the division algebra over QP of Hasse invariant a half. And on P1, the stratification is given by the rational points of P1 and its complement, which is the Drinfeld upper half plane. And sorry. And on the modular curve, the good reduction locus, you get a stratification into the ordinary locus and the supersingular locus, where, so here this is the small confusing point. So namely that I was alluding to about the higher rank points. So, so here, this ordinary locus on the generic fiber is defined in a way that you say a test object mapping to the good reduction locus of the modular curve lies inside this ordinary locus if so from this this point you get a elliptic curve over R plus sharp, but you look at the reduction so of its base change to R circ sharp mod P. And if this thing is ordinary, then you say that this point lies in this ordinary locus. So, so this is slightly different from the stratification you would obtain by looking at specialization map from the p-adic generic fiber to the special fiber and pull back the natural stratification from the special fiber. Because in that case, you would genuinely look at the reduction type of E over the close point of split R plus. So in particular, if you define it this way, this stratum is closed and this one is open. So the supersingular locus is similar. And the last thing is that if you look at the stratum on the Igusa stack, then you will see, not surprisingly, the Igusa varieties. The V sheaf attached to some perfect Igusa variety and then modulo GB tilde action. And there is again a difference coming from higher rank points, etc. So I will put a bar on both sides to make them. So this is the canonical compactification of Huber to make them insensitive to higher rank points. So I'll finish by defining what this Igusa variety is. So where for B being ordinary or supersingular, we can fix a representative of a p-divisible group over FB bar in the corresponding isogeny class. And So if you look at the special fiber of the modular curve at hyperspecial level, then it has this stratification of ordinary and super singular locus. And over each locus, you can consider the tosser of trivializations of the universal p-divisible group with this fixed one. And this is represented by a perfect scheme and will be the Igusa variety at the corresponding level. So this is a tosser under automorphism group scheme for XB, but in fact, a larger group acts on this thing, namely the group of self-quasi-isogenies of XB acts on here. So I will just denote by XB tilde for the universal cover this way. And in fact, if you take the diamond attached to this thing, this is an isomorphic to this GB tilde. So there you get the description of the Igusa stack above, which also explains why we name this object Igusa stack, because it interpolates Igusa varieties from across the Newton stratification. And if you rewrite the Cartesian diagram for each stratum in terms of these objects, then you will recover the p-adic basic uniformization of rubber zinc as well as Manteufel's product formula. So I'll stop here.
Okay, thank you very much. Are there some questions?
What is XB tilde in the formula?
The question is, what is XB tilde in the formula?
What's the, which?
Sorry.
XB tilde? I guess here in this last formula.
Okay, sorry. This XB tilde is the universal cover of XB. Just inverse limit along the multiplication by P maps on XB.
Yeah. Is there anything that, there any extension of this away from the good reduction locus?
Yes, I mentioned at the beginning that Daniel will probably explain this. It follows from his work that you can extend away from the good reduction locus.
Can you say anything? Oh, he'll talk about it, but never mind.
Sorry, can I say?
No, never mind. Maybe, well, I was just going to say GL2. Can you say anything about what it looks like for GL2 in the spirit of your talk?
So basically, what basically, if you take I'll make a small assumption, which is not allowed in this case. So basically, you can construct a minimal compactification of the Igusa stack, which will appear in Anna's talk, and then if you pull back to the flag variety, that gives you the minimal compactification of the Shimura variety. And inside there, of course, the open part, so the full Shimura variety, so beyond the good reduction locus, sits as a subspace. So you can just look at the image of, maybe I can write something. So you can just look at the image of that in the minimally compactified Igusa stack. This will be the extension. And in Daniel's talk, he will explain how you get this guy by specifying some relation over this Shimura variety.
So do Igusa stacks give any new intuition as to why this kind of switching of the strata happens, sort of between the special fiber stratification and sort of the internet level stratification? So why?
Well, this thing I kind of explained. It's just a matter of how you define the stratification.
Some other natural one. I mean, if it from Igusa stacks is the opposite. So if the higher ranked points switch allegiances from one to another.
So the point is that if you define the stratification from pulling back from the stratum from Bangji, then you will only see like the one that is insensitive to higher rank points. And of course, you can define another stratification on the Igusa stack just according to maybe the isogeny type of the close point on the general test object, and that will pull back to the the one you would expect it. But yeah.
Okay, thank you again.